Yes, guys, this is the typical block diagram for the SR type DVM. See, one thing you remember, we are discussing this one under the heading of commonly used principles of ADC. In the last class, we discussed about this compensation techniques. One is a direct compensation that we have did with the help of staircase type, ramp type DVM. And this one is a SAR type, successive approximation type DVM. So two main blocks are coming here. One is sample and hold circuit, and another one is this SAR block along with DAC. Except that this main gate will be there, comparator will be there, and this oscillator will be there along with the counter. They are all playing their roles as usual, as we have seen in case of this direct compensation type technique. So sample and hold circuit, what it is doing, it's simply going to cut your continuous time signal into small number of samples decided by this RC time constant. And each of these samples will be held for the time being and applied to this gate here with the clock to be counted and to be converted to the analog with respect to the reference, and again get back to be compared with the VN. So as and when until VN is equal to V8, this process, this loop is going to continue. ಪ್ರತಿಯೊಂದು ಸ್ಯಾಂಪಲ್ ಇಲ್ಲಿ ಗೇಟಿಗೆ ಅಪ್ಲೈ ಆಗ್ತೈತಿ ಆ್ಯಂಡ್ ಒಂದು ಪಲ್ಸ್ ಇಲ್ಲಿ ಹೋಗ್ತೈತಿ. ಮೀನ್ಸ್ ಒಂದು ಸ್ಯಾಂಪಲ್ಗೆ ಒಂದು ಪಲ್ಸ್ ಹೋಗ್ತೈತಿ, ಒಂದು ಸ್ಯಾಂಪಲ್ಗೆ ಒಂದು ಪಲ್ಸ್ ಹೋಗ್ತೈತಿ. ರಿಂಗ್ ಕೌಂಟರ್ ಕೌಂಟ್ ಮಾಡ್ತೈತಿ. ಆಮೇಲೆ ರಿಂಗ್ ಕೌಂಟರ್ ಒಂದು ಸ್ಯಾಂಪಲ್ ಸಿಕ್ಕ ಮೇಲೆ ಒಂದು ಕೌಂಟ್ ಮಾಡಿದ್ಮೇಲೆ ಒಂದು ಸಿಗ್ನಲ್ ಕಳಿಸ್ತೈತಿ SCRಗೆ. SCR how it is going to work out, already we discussed this one. ಅದು ಇದೆಲ್ಲ ತಗೊಂಡು ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ದೇವಲ್ಲ ಅದು. ಓಕೆ, ಕಮ್ ಬ್ಯಾಕ್ ಟು ದಿಸ್ ಒನ್. SCR ಏನು ಮಾಡ್ತೈತಿ, ಇಲ್ಲಿ ನೆಟ್ವರ್ಕ್ ಆಫ್ ರೆಜಿಸ್ಟರ್ಸ್ ಇರ್ತಾವ. those registers ಏನು ಮಾಡ್ತಾವೆ, they will help you to convert your analog to digital 8-bit DAC ಯೂಸ್ ADC ಯೂಸ್ ಮಾಡಿದ್ರು DAC. ಇದೇನು ಮಾಡ್ತೈತಿ, ಅನಲಾಗ್ ಡಿಜಿಟಲ್ ಟು ಅನಲಾಗ್ ಕನ್ವರ್ಷನ್ ಮಾಡ್ತೈತಿ ವಿತ್ ರೆಸ್ಪೆಕ್ಟ್ ಟು ದ ವಾಟ್ ರೆಫರೆನ್ಸ್ ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಗಿವ್. ನನಗೇನು ಅನಲಾಗ್ ಇಲ್ಲಿ ಬಂದ ಮೇಲೆ ಅದು ಇನ್ಪುಟ್ ಸ್ಯಾಂಪಲ್ಸ್ ಜೊತೆ ಕಂಪೇರ್ ಮಾಡ್ತೈತಿ ದಿಸ್ ಕಂಪರೇಟರ್. ಸೊ ನಾವು ನೋಡಿದ್ದೇವಲ್ಲ ಸಕ್ಸೆಸಿವ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್, ಪ್ರತಿಯೊಂದು ಸ್ಟೆಪ್ ನಾವು ಏನು ಮಾಡ್ಕೋತ ಹೋಗ್ಯವಲ್ಲಿ 10-bit ADC ತೊಗೊಂಡಿದ್ದೇವಲ್ಲ, 2 to the power -1, -2, -3, -4. ಅಂದ್ರಲ್ಲಿ ಆ್ಯಕ್ಚುಲಿ ಏನು ಮಾಡತ್ತೀವಿ ನಾವು, 2 to the power -1 ಅಂದ್ರೆ 1/2. ಗೆಟಿಂಗ್ ದಿಸ್ ಒನ್, 2 to the power -2 ಅಂದರೆ 1/4. ಮೀನ್ಸ್ ಪ್ರತಿ ಸಲ ನಾವು ಡಿವೈಡ್ ಬೈ 2 ಮಾಡ್ಲತ್ತೇವೆ. ಆರ್ ಯು ಗೆಟಿಂಗ್ ದಿಸ್ ಪಾಯಿಂಟ್? ಪ್ರತಿ ಸಲ ಫಸ್ಟ್ ಏನು ಮಾಡಿದೆ, 2 to the power -1, ದಟ್ ಇಸ್ 1/2. ಮೀನ್ಸ್ ರೆಫರೆನ್ಸ್ ಏನಿತ್ತು 1/2 ಮಾಡಿದೆವು, 0.5 ಬರ್ತದೆ. ದಟ್ಸ್ ವೈ ವಿ ಆರ್ ಕಂಪೇರಿಂಗ್ ದೇರ್ 0.6 ವಿತ್ 0.5. ಇಲ್ಲಿ 0.6 ವಿತ್ 0.5 ಕಂಪೇರ್ ಮಾಡ್ತೀವಿ. ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಹೋದಾಗ 2 to the power -2 ಆಯ್ತು ಅಂದ್ರೆ 1/2, ಅನದರ್ ಡಿವೈಡ್ ಬೈ 2, 1/2, ದಟ್ ಇಸ್ 1/4. ಲೈಕ್ ದಟ್ ಸಕ್ಸೆಸಿವ್ಲಿ ಪ್ರತಿ ಸ್ಟೆಪ್ ನಾವು ಡಿವೈಡ್ ಬೈ 2 ಮಾಡ್ಕೊತ ಹೋಗ್ತೇವೆ, ಅದರ ವೇಟ್ ಚೇಂಜ್ ಆಗ್ಕೊತ ಹೋಗ್ತೈತಿ. and thereby successfully compare each sample with comparing with the input and adjusting its value so that it can reach nearer to the 0.6. ಲಾಸ್ಟಿಗೆ ನೋಡಿರ್ಬೋದಲ್ಲ 0.6 ವ್ಯಾಲ್ಯೂ ಡಿ ಟು ದಿ D0 ಬಿಟ್ ಎಷ್ಟು ಸೆಟ್ ಮಾಡಿದ್ದೇವೆ, ಅದರ ಅನಲಾಗ್ ಔಟ್ಪುಟ್ ವ್ಯಾಲ್ಯೂ ಎಷ್ಟು ಬಂತು, 0.59 and something we got. So like that with successive approximation, every step will go on approximating each sample, this one, so that will arrive at the nearest value with the help of this loop. This loop is continuing like that. The recursive ಹೋಗ್ತಿರ್ತೈತಿ depending on how many steps we need, depending on how many bits ADC you are using. This SAR networking ladder also I have discussed how it is helping us to convert digital to analog version like this one. So this one I took the example in the last class. Input what I want to convert here, it is a 0.6 with the reference of 1 volt. Here you can see this diagram, it is clear. So 10 bit deki 1 volt reference kottite. So input here it is the thing what we want to convert is 0.6. So that I need to compare every time with the 0.5. Okay. So only this much will be given in the exam to let you to design EDC and get it converted to analog. So let us see the steps here. So weights I have written here from left to right for 10 bit EDC, from left to right, that is from D9 to D0. The table ಹಾಕೋಬೇಕು ನೀವು. Right, D9, D8, D7 and D0 because 10 bit EDC is the question. And weights you can see I am writing from left to right, beginning from left 2 to the power minus 1. Why 2 to the power minus 1? First time I have to divide this reference by 2. That's why it is 2 to the power minus 1 I have written. That will become a weight for D9. And that I need to compare. Means ಇಲ್ಲಿ ಏನು ಮಾಡತ್ತೀನಿ ಅಂದ್ರೆ 0.6 is the first time compared with 1 volt divided by 2. That is 0.5. Now it is 0.6 input is greater than this V reference by 2. That is 1 volt by 2. That is 0.5. Greater than this. That's why I am going to set D9 to 1. That's all. Next you can see this will be applied to that AND gate. Clock pulse is applied. Ring counter is going to count that pulse. And it is going to signal your SAR to go proceed with the next step. It is going to go digital version, that is a 8 bit ತೋರಿಸಿದ್ವಿ, actually 10 bit in question to be converted to analog. ಅದು next ಇಲ್ಲಿ ಬರ್ತದೆ, next ಇಲ್ಲಿ analog ಆಗಿ ಬರ್ತದೆ. So next you can see how much we are getting for 2 to the power minus 2. ಈ previous step ಏನಾಗಿತ್ತು 1 volt ಇದ್ದದ್ದು divided by 2 ಮಾಡಿದ್ರೆ 0.5 ಇತ್ತು. In next step D80 ನಾವು ಇದೀವಿ, ಇಲ್ಲಿ ಬಂದ ಮೇಲೆ again will divide that 0.5 by 2 ಅರೆ ಮಾಡ್ರಿ, ಅಥವಾ 1 volt by 4. ಯಾಕೆ 1 volt by 4? ಫಸ್ಟ್ ಸ್ಟೆಪ್ನಾಗ 1 volt by 2 ಮಾಡಿರಿ, by 2 ಮಾಡಿರಿ. ನೆಕ್ಸ್ಟ್ ಸ್ಟೆಪ್ another by 2. First step by 2, another by 2. It is 1 by 4. That's what is 2 to the power minus 2. Let me pause here. Are you getting this one? Can anyone respond me? Hello? Are you getting this one or not? Up to this. How we are getting the weights here? How I am assigning the weights? 2 to the power minus 1. Why? 2 to the power minus 2. Why? Tell me. Shall I repeat? Anybody is there? You need to respond, otherwise I have to stop here itself. Are you getting this one, or shall I repeat, or what you have to tell? Other, if you keep quiet, what I have to understand?
Yes, sir. Getting. Yes.
Pardon? Okay, you are getting, okay. Only you are responding. What's about others? Any new voice? Any new voice? Anybody else, whether you are getting or not? Some people are leaving here. I am observing the number of strength is reducing now. Notes 34. Out of 44, notes 34. This is not the attitude of your professional course you are joining. This is not the attitude you should show. This is not the respect you are giving towards the future. Now it's again decreasing, showing 33 members, means 30 members. It will simply indicate that you people are not at all interested in doing the engineering forcibly. So don't do anything forcibly in the life that it will not give you anything back. Don't even pretend to do doing something. You do what you like. That's all. It's very simple. Of course, that will give you the result. Okay, no any response I am getting. This is the kind of attitude we have about the students here. So they don't want. They simply want marks. So one thing, guys, if you run behind the marks, you will get zero. Zero in the life. Knowledge will be zero. So without knowledge, it is very difficult to survive in the market. So after COVID, you can see a lot of opportunities are coming. Still, the opportunities are gaining very, very high. Without knowledge, it is very difficult. I cannot pay you if you don't have any knowledge. As being a company, if they are thinking, you should tell what skills you have. Then only you are sellable. Just coming back to this one, the problem given here is that input 0.6 volt need to be converted to analog with the help of a DAG, 10-bit DAG, reference voltage is 1 volt. So D0 to D9, this table you have to make out. The first time input to 0.6 volt need to be compared with not 1 volt, it should be divided by 2, that is V reference by 2, that is 1 volt by 2, that is 0.5. That's how I have shown here. Zero point 0.6 is now compared with 0.5 with help of this comparator. So this 0.6 you are getting from Champaland volt and this 1 volt you are getting from the DAG, that is ACR section. This is the comparator. Now we are getting 0.6 greater than 0.5 and get output here, the comparator output will be high. That is going to enable the gate here below this. You can refer to this diagram and let the clock pulse to be counted by the counter, and counter will send the feedback to the SAR section to go for next step, divide by 2, that is 2 to the power minus 2, again another divide by 2, that is 1 volt by 4 if you want you can do, or you can do 0.5 by 2. That's what we are doing here. So now here what we are doing in the next step, your that SAR section, now we are this 0.6 is fixed. Now this one will be again divided by 4. So what we are getting, the previous bit which was set, no, its weight we have to consider here, zero point 0.5 plus the present bit what we are getting 2 to the power minus 2, 0.25, that will be added with this. Why we need to consider the previous weight? Because the last bit was set, that we have to consider. That's why it is known as successive approximation. It's a cumulative one, but while doing cumulative, we have to consider the weight where the last bit was set. This you underline the sentence. We have to cumulatively go on adding or dragging that weight where the last bit was set. This is very important. So that's why we are adding here. You can see 0.5 is the weight where the last bit, the D9 bit was set. We have to cumulatively add here with the present weight, that is a 0.25. We will get 0.75. Now this 0.75, if we compare to the 0.6, no, so 0.6 will never be greater than 0.75. Hence we are not going to set D8 bit. So D8 bit will be reset, that is 0. Initial all are set, you can see here, I have shown in the table. That's why D8 will be 0. Okay. So again, you can see the comparator output. It will be showing that unequal output. Again, it is 1. clock pulse will be applied to the ring counter. It is going to count the pulse, going to send the feedback to SCR, register network. Go for next step to converting, that is next sample, that is 2 to the power minus 3 weight. Again divided by 2. So what is the last weight? That is a 0.5, again divided by, sorry, 0.75, that divided by 2. Or if you want, you can do 1 divided by 8 now. 1 divided by 8, if you do, how much will get? 0.125. 0.125 or 2 to the power minus 3 will give you the present weight. And previous weight is what? Previous weight is the where that weight where the last bit was set. Last bit set was D9, not D8. D8 0 near. So 0.5, again it will be added with the present weight 0.125. So I will be getting now 0.625. Now you can see 0.6, it is nearly coming closer to 0.625 is nearly coming closer to 0.6 compared to the previous 0.75. This is how it is successfully trying to approximate with the 0.6. So again 0.6 is not happens to be greater than 0.625. Again D7 will be set to 0. Okay. So again, the loop is continuing here. The main gate will be letting the another clock pulse applied to the counter to be counted, and the ring counter will send the feedback signal to the SCR section. Again, we are going for the next step, that is 2 to the power minus 4. That is 1 by 2 to the power 8, or you can say 1 by 8. Sorry, 1 by 16. That is 0.0625. This is the present weight will be added with cumulatively with the weight where the last bit was set, that is a D9 bit was set, that is a 0.5. Now if you add this, what is the cumulatively added updated weight is 0.5625. Now we can see compare 0.6 with greater than 0.5625. Then we are going to set D6 to 1. Okay. Next you can continue with the next, that is a D5, the table here. Its weight is going to be 2 to the power minus 5. Means we have to divide successively by another 2. Or we can do 1 by 32. That will give 1 by 0.0314. Then we can, this is the present weight. What is the present weight? 1 by 2 to the power 5. Or present weight will be 1 by 32. 2 to the power 5 ಎಷ್ಟು ಆಗ್ತದೆ 32 ಆಗ್ತದೆ. So 1 by 32 ಮಾಡಿದ್ರೆ ಎಷ್ಟು ಬರ್ತದೆ 0.03125. This is the present weight at D5 position. That you have to add with the previous weight where the bit was set. Last bit was set. Last bit was set D9 like D6 bit set ಆಯ್ತು. So last bit set D6 ಆಗ್ತದೆ, not D9. So 0.5625 we have to cumulatively add with the present weight, that is a 0.03125. Are you getting this one? Please, anyone tell me. So this step.
Yes, sir.
Yeah. Okay. Thank you for your feedback. Now that's why you can see this 0.6, it is fixed still. Now we are comparing with this cumulatively updated new weight, that is a 0.59375. Now 0.6 will become with the greater than 0.59 aito. Now we'll have to set D5. Okay, continuing this. So here we are. So we'll set the D5 to 1. What? Okay. Go for next, that is a D4. Its weight will become 2 to the power minus 6. Its present weight will be decided by this 2 to the power minus 6. And the rest ಆಗ್ತದೆ 1 by 64. So 1 by 64 will be the present weight. That is a 0.015625. So this present weight we have to add with cumulatively, we have to add with the weight where the previous base bit, last bit was set. Last bit ನಮ್ದು D9 ಅಲ್ಲ, D9 ಆದಮೇಲೆ D6 ಸೆಟ್ ಆಗೈತೆ. D6 ಆಗಂಗಿಲ್ಲ, ಯಾಕಂದ್ರೆ D6 ಆದಮೇಲೆ D5 ಸೆಟ್ ಆಯ್ತು. So D5 is the last bit which was set. So ಅದರದ್ದು weight ಏನಿತ್ತು 0.59375. So this will become the cumulatively we are going to add the weight where the last bit was set. So this weight we have to add cumulatively with the present weight, that is 0.015625. Are you getting this one?
Yes, sir.
Yes, sir.
Yeah. Now we can see
Yes, sir.
one. Yeah, okay. Point 0.6 is now you have to compare it to 0.609375. So this is not going to be greater. So we'll reset D4 to 0. Where is D4? Okay, D4 will be reset. Okay, ಮೊದಲೆಲ್ಲ set ಮಾಡ್ಕೊಂಡಿರ್ತೀವಿ ನಾವು. Now we'll have to reset. Again, that loop will continue. The comparator, the main gate, ring counter will count the pulse and will send signal to SCR section. Again, we are coming back to 2 to the power minus 7. That is about the D3 position. D3 we are now here. It was set already, default. Now we have to decide whether we have to retain 1 or 0. Its weight is now going to be what? 2 to the power minus 7. So 2 to the power minus 7 means how much will get? It is going to be 32, 64, 128. Okay. 1 divided by 128 you have to do. So how much will get? 0.0078125. Now this one is going to be your present weight, current weight at a D3 position. At a D3 position, the current weight is going to be 2 to the power minus 7. Plus we have to add the weight cumulatively where the previous bit was set. Our previous bit was set at D5. D5 set ಆದ್ಮೇಲೆ ಮತ್ತೆ ಯಾವುದೇ bit set ಆಗಿಲ್ಲ, D4 reset ಆಯ್ತು. Now we are in D3. Means our previous bit set was D5 only, not a D6. Last bit set ಆಗಿದ್ದು D5 D6 ಆಗಿಲ್ಲ. So what's the weight it into 0.59375. So that you add cumulatively with the present weight, that is 2 to the power minus 7, that is 0.0078125. How much will you get? 0.6015625. Now this you compare with the 0.6 here once again. ಸೊ ಇದೆಲ್ಲ ಯಾರು ಮಾಡ್ತಿರ್ತಾರೆ? SCR ಮಾಡ್ತಿರ್ತದೆ. ರೈಸ್ ಟು ನೆಟ್ವರ್ಕ್, ಆಮೇಲೆ 10 ಬಿಟ್ ಡ್ಯಾಕ್ ಅವೆರಡು ಕೂಡಿಸಿ ಇವೆಲ್ಲ ಮಾಡ್ತಿರ್ತಾವೆ ಇದೆಲ್ಲ ಕೆಲಸ. Now again comparison will be done by this triangular section. 0.6 is greater than 0.6015? No. Again we are going to reset D3 to 0. Default set it, will reset it to 0 because 0.6 is not happens to be greater than 0.6015625. Next again comparator unequal inputs, XOR gate, one set, AND gate is on, sending next clock pulse to ring counter, it is counting one pulse, sending feedback signal to SCR and DAC section. SCR DAC section, next they will go to D2 position. Now we are here. Its weight again you can see it's going to be 2 to the power minus 8. So it's going to be 128, 256. So present weight is decided by 1 by 256. You do with calculator, we'll get 1 by 256 as 0.0039065. Calculator ಇಟ್ಕೋಬೇಕು ಮೊದಲು ಅಂದ್ರೆ ಗೊತ್ತಾಗ್ತದೆ. So this is going to be the present weight for D2. ಇದು present weight ಜೊತೆ ನಮ್ದು previous weight where the last bit was set, D3 set ಆಗಿಲ್ಲ, D4 set ಆಗಿಲ್ಲ. So last bit set was remaining D5 only. ಅದರದ್ದು weight ಏನೈತಿ 0.59375. It will be remaining same. You can see here arrow mark I have shown. We are using the same weight since last two steps. This is the third step. Again we are using the same weight because the last bit set was only D5, not D6. So if you add this one, so ಇದೆಲ್ಲ ಟ್ರೇಸಿಂಗ್ ಮಾಡೋದೆಲ್ಲ SCR DAC ದವ್ರು ಮಾಡ್ತಿರ್ತಾರಲ್ಲ, add ಮಾಡಿ with the present weight, that is 0.00. So where we are, sorry, I am here 0.0039065. What I will be getting? 0.59765625. Calculator ಒಳಗೆ ಎಷ್ಟು ಡಿಜಿಟ್ ಬರ್ತೋ ಎಲ್ಲಾನು ಬರ್ಕೋರಿ. That is very important. Significant digits are very important because these digits are going to tell you how closely you are approaching with this 0.6. That's what successive approximation. That SCR DAC ಅವು ಅದೇ ಕೆಲಸ ಮಾಡಲಾತವೆ. They are trying to successively approximating and going very much closer to 0.6 with the 10 bit TDC or DAC. Now you can see 0.6 happens to be greater than 0.5976 etc. Hence we will set D2 to 1. Understand? Now you can see D2 is now set after D5. D5 ಆದ್ಮೇಲೆ D4 set ಆಗಿಲ್ಲ, D3 set ಆಗಿಲ್ಲ. Now D2 got set. In further step ಗೆ ಇದೇ weight ನಾವು use ಮಾಡಬೇಕು to cumulatively add in the present weight of the further steps. Now next D1 position, its weight will be 2 to the power minus 9. 256 means 512. 1 by 512 ಮಾಡಿದ್ರೆ in the calculator. So we will get 0.001953125. Okay, this is the present weight. Plus cumulatively it should be added with the weight where the last bit set was now D2, not D5. That is going to be 0.59765625. We'll get updated weight at D1 position will be 0.59960937. This you compare with the 0.6, obviously it will become greater. We'll set D1 to 1 to 1. Again loop will repeat because it is 10-bit DAC or EDC will be there. 2 to the power minus 10. You do that one with the calculator. So the present weight happens to be 0.0009765663. This present weight will be cumulatively added with the weight of where the previous bit was set, that is D1 was set, not D2. So D2 ಆಗಲ್ಲ, D1 ಆಗ್ತೈತೆ. Last bit set, last recently bit set 0.59960937. Add with this, so we'll get updated weight at D naught going to be 0.600. So we can compare 0.6 with 0.60058. It is not going to be greater. Again D naught will be reset. So the digital equivalent for the 0.6 what we are getting by ADC is going to be 10011001110. So what is the approximated analog version we are getting for 0.6 using 10-bit ADC is going to be 0.59960937. So if you find out the error here, 0.6 minus 0.59960937, you are able to find out absolute error, relative error and percentage error. Even you can also calculate accuracy. Got this point? Anybody?
Yes, sir.
Okay. Now your
Yes,
job.
sir.
Yeah. Okay. Now shall I repeat once again, or what the things are clear?
Clear, sir.
Shall I repeat? Okay. Hope the things are clear. So tell me whether things are clear or not. That's what I asked. Otherwise, I am ready to repeat this because this problem design is very important. Anybody boys side?
So repeat.
Yes, once again, I am repeating this. We are using 10-bit ADC. We have given 0.6 to be converted with the help of 1 volt reference as a DAC given there. 10-bit ADC means you have to put this table from D0 to D9 like this. At D9 we will get the weight 2 to the power minus 1. You can see here you have to focus on these two inputs only. That's why I have drawn this one. You keep this diagram in mind. The first time at D9 position, I am comparing 0.6 with not 1 volt. 1 volt divided by 2. That is 2 to the power minus 1. Every step I am go on dividing it by 2. Okay. So 0.6 is now compared with not 1. It is 1 by, that is a 0.5. So 0.6 is greater than 0.5. Hence D9 will be set. Okay. Next we'll go for the D8 position. Its weight is again another divided by 2. that is 1 node by 2 and by 2, that is 1 node by 4, that is 2 to the power minus 2. So this will become the present weight 0.25. So this will be added cumulatively with the weight where the last bit was set. Last bit set was D9, its weight was 0.5. Now you can add cumulatively this 0.5 with the present weight 0.25. So we'll get the updated weight 0.75. Now this updated weight you have to compare with the 0.6. Obviously 0.6 will never become greater than 0.75. Hence D8 will be reset. Okay. Next you go for D7 position. Okay. So we'll go for D7 position. Again you divide by 2. So how many divided by 2 so far? I am in the D7 position, third position from left to right. Means I did divide by 2 3 times. 1 by 2, 1 by 2, 1 by 2 means how much I got? 2 to the power minus 3. Is it clear? Sayar?
Has
Yeah. So now boys have to respond. So 2 to the power minus 3. This will become the present weight for the D7 position. 2 to the power minus 3, that is 1 by 8 ಮಾಡಿ the rest ಬರ್ತೈತಿ 0.125. This is the present weight at D7 position. Now this present weight you have to add with, cumulatively you have to add with the weight where the last bit was set, not reset, set. D8 set ಆಗಿಲ್ಲ, D8 set, D9 set. ಅದರದ್ದು weight ಏನದು 0.5. ಅದೇ ವೇಟ್ ಯಾಕೆ ತಗೋತೀವಿ? ಯಾಕಂದ್ರೆ D9 ಬಿಟ್ ಸೆಟ್ ಆಗಿದೆ. ಸೆಟ್ ಆಗಿದ್ರದ್ದು ವೇಟ್ ಅಷ್ಟೇ ತಗೋಬೇಕು ನಾವು, ರಿಸೆಟ್ ಆಗಿದ್ದಿಲ್ಲ. That's why I am cumulatively adding 0.5 where D9 was set, last bit was set with the present weight 0.25. So updated weight ಎಷ್ಟು ಬಂತು? 0.625. Now this updated weight 0.625 you have to compare with the 0.6 here. So obviously 0.6 is not greater than 0.625. Hence again you reset D7 to 0. Okay, go for next position, that is D6. Again divided by 2. D6 ಅಂದ್ರೆ ಎಷ್ಟನೇ position? At 1 2 3 4. 4 times are divided by 2 means 1 by 2 1 by 2 1 by 2 1 by 2 means 2 to the power minus 4. What is the present weight at D6? 2 to the power minus 4 ಎಷ್ಟು ಬರ್ತೈತೆ ಕ್ಯಾಲ್ಕುಲೇಟರ್ ಅಲ್ಲಿ? present weight at D6 position 0.0625. It is the present weight. Present weight compare ಮಾಡಂಗಿಲ್ಲ ನಾವು. Present weight ಜೊತೆ we have to add cumulatively with the weight where the last bit was set. D9 ಯಾಕೆ D8 set ಆಗಿಲ್ಲ, D7 set ಆಗಿಲ್ಲ ಇನ್ನ. 0.5 we have to add. So the updated weight what I am getting? 0.5625. So this updated weight 0.5625 should be compared with the 0.6. Obviously it is greater. That's why we are setting D6 to 1. Sayed, is it clear?
has
Yeah. Then after setting D6 to 1, go for next position D5. D5 here. ಇಲ್ಲ D5 ಅಂದ್ರೆ 8ನೇ ಸಲ ನಾವು ಡಿವೈಡ್ ಬೈ 2 ಮಾಡಬೇಕು. 1 2 3 4 and 5. So it is the fifth time I am dividing by 2. 1 by 2 1 by 2 1 by 2 1 by 2 and 1 by 2. 5 times I did 1 by 2 means 2 to the power minus 5. This will give the present weight at D5 position. ಅದೆಷ್ಟದ 0.03125. present weight ಎಷ್ಟು ಬಂತು? 0.03125. Now this present weight we have to add cumulatively with the weight where the last bit was set. Last bit, last recent, latest, not D9. Now it is going to be D6. D9 ಆದ್ಮೇಲೆ D6 set ಆಗಿದೆ. ನಾವು D9 weight ಯೂಸ್ ಮಾಡಬಾರ್ದು ಈಗ. D6 weight ಲಾಸ್ಟ್ ಲೇಟೆಸ್ಟ್ ಒನ್ ಸೆಟ್ ಆಗಿದೆ ಇದೆ 0.5625. ಇದನ್ನು ಯೂಸ್ ಮಾಡಬೇಕು. Now this weight we have to add with the present one. Updated weight ಎಷ್ಟು ಬರ್ತೈತಿ? 0.59375. Now this you compare with the 0.6. Obviously it becomes greater. We set D5 to 1. Is it clear? Next we'll go for D4. It is the sixth time I am dividing by 2. 2 to the power minus 6. Here D4. Present weight will come 0.015625. Added cumulatively with the weight where the last bit was set. D5 ಬಿಟ್ಟು ಸೆಟ್ ಆಯಿತು, ಅದಕ್ಕಿಂತ ಮೊದಲು D6 ಸೆಟ್ ಆಗಿತ್ತು. ಲೇಟೆಸ್ಟ್ ಆಗಿ ಸೆಟ್ ಆಗಿತ್ತು ಲಾಸ್ಟ್ ಒನ್ ಯಾವುದು D5 ನಾಟ್ D6. ಲೇಟೆಸ್ಟ್ ರೀಸೆಂಟ್ is going to be D5 not D6. Sayed.
Yes, sir.
Is it clear?
Yes, sir.
So this weight you have to add with 0.015625. Updated weight what you are getting 0.609375. So this we have to compare with the 0.6. Obviously it is not greater, hence you have to reset D4 to 0. Next we'll go for D3 position here. The seventh time I am repeatedly dividing it by 2. There is 2 to the power minus 7. This 2 to the power minus 7 will give me the present weight. That is 0.0078125. Add cumulatively with the weight where the last bit was set. Last bit D4 set agilla, but adakkiಂತ ಮೊದಲು ಯಾವುದೈತಿ, that is the latest D5. ಅದೇ weight we have to continue with cumulatively adding here. Okay, means we have to add 0.59375 with 0.0078125. What you will get? 0.6015625. This you compare with 0.6. Obviously it is not greater. Reset again, D3 will be reset. Next to go to D2. It is the 8th time I am repeatedly dividing it by 2. That is 2 to the power minus 8. That will give my present weight. That is going to be 0.0039065. Now this present weight will be added cumulatively with the weight where the last recent bit was set. Again it is D5 only because D4, D3 resetted. So we'll get updated weight at D2 position will be 0.59765625. This updated weight you have to compare with 0.6. Obviously it will become greater. You have to set D2. See here D5 ಆದಮೇಲೆ D4, D3 set ಆಗಿಲ್ಲ. Now D2 got set. In further step ಈಗೆಲ್ಲ D2 ದ updated weight use ಮಾಡಬೇಕು ನಾವು cumulatively add ಮಾಡಬೇಕು. Now in a D1 position for the 9th time repeatedly I am dividing it by 2. That is the reference voltage. That is 2 to the power minus 9. That is 0.00153125 will become the present weight. This you add present weight with the cumulatively with the weight where the last bit that is D2 was set. That is 0.59765625. We'll get it as 0.59960937. See, it is very much becoming closer to the 0.6. Hence, it becomes greater. We'll set the D1. Go for the 10th one. Repeatedly, I am dividing it by 2 at a D0 position. 2 to the power minus 10. That is 0.000976563 will be the present weight. Add this with cumulatively with the weight where the last bit was set, D1 was set. You will get updated weight as 0.60058 something. Obviously, you compare this updated weight to 0.6, not greater. Hence, you set reset D0 to 0. So the digital equivalent for the 0.6 is going to be 10011001110. And its analog version will be 0.599609375. Now you can compare this with 0.6, find out the error, absolute error, relative error, percentage error, relative accuracy, all the things you can find out. You can come out with the accuracy of this 10-bit ADC. Similarly, same problem I will give you given you the practice for the last session only. At least now you can do same. Instead of 10-bit ADC, you can repeat this with 8-bit ADC 12-bit ADC, and in each case you can find out error and accuracy, and you tell me in the next class in which case you are getting less error and more accuracy. Is it clear, Sayyid and others?
Yes, sir.
So hope you are confident you are able to do what practicing I am giving. Same problem, repeat it for 8-bit, 12-bit, and this 10-bit already I did, and find out the what you can do, error and accuracy. In which case you can tell me you will be getting more error, less accuracy. In which case you are getting less error and more accuracy. Hope you can do this one. Anything you want to ask in today's session before we will conclude? Because I wanted to devote this second session also for this design problem, because this is very important. So in internal or exam, I may not ask the same thing. So I may ask you to do with 8 or 10 or 12 bit EDC with a different VN and reference. Hope you are competently do it with practicing what I am giving. At least you understood the methodology how to do this one systematically. You can use the table and diagram, and also you can use these calculations. Arrow mark I have shown here, right mark, cross mark I have shown only to let you to understand. Don't do that in your presentation answers. So practice it. Hope you can do it. Next class you can tell me the answers. So next class will continue with the further devices which is there for your syllabus. But before that, next thing, let me finish up the small thing. The same thing I did here. Resolution and sensitivity. So normally with respect to DVMs, digital voltmeters, we are discussing resolution. It will indicate indirectly it is related with, indirectly or directly in some way it is related with significant digits, means how many decimal things or digits totally before or after decimal point your display is able to display. So normal formula for the resolution for the display of DVMs is going to be 1 by 10 to the power n. N here it will indicate number of full digits. So how many total number of digits your DVM is going to display? That is called full digits. So for example, the resolution of DVM with n equal to 3 active digits is going to be 0.1 percentage. This is how we mean by resolution. Sensitivity means it is Fs minimum into R resolution. Fs minimum is lowest full scale of meter. Okay, so we'll see some numericals. What is the resolution of a 3.5 digit display on 1 volt scale or range and a 10 volt scale or range, like that? This problem is asked. Listen here carefully. What is the resolution of 3.5 digit display? So display ಏನು ಮಾಡ್ತದೆ 3.5 digit display on 1 volt range, that is separate, and 10 volt range separate. So the number of full digits ಎಷ್ಟು ಅದಾವ 3 ಅದಾವ. ಇನ್ನೊಂದು half digit, that is not a full, it is half. Full digits ಎಷ್ಟು ಅದಾವ 3 ಅಷ್ಟೇ. So resolution how much will get 10 to the power n, 1 by 10 to the power n. So full digits ನಮಗೆ ಕೊಟ್ಟಿದ್ದ ಪ್ರಕಾರ 3.5 ಅಡು 3 ನೇ ಆಗ್ತಾವೆ. So we can substitute, very simple, we will get 0.001. If you want to express in percentage, simply multiply it by 100. So we will get 0.1 percentage. Now coming to the range, two ranges he has given. The meter cannot differentiate between the values that differ by less than 0.001 full scale. That is the meaning. Resolution means if you want to measure anything 0.001, anything less than 0.01, it will not show. Minimum value is this much only. Kadmi value you measure it will not show. It will show only 0.001. because it is the minimum value that it can respond, lowest value that it is sensitive to the lowest change, least count you can say. So for the full scale range of 1 volt, R equal to, for 1 volt it is 1 into the least count, that is a 0.00. For 10 volt it will be 10 into 0.001, 0.01. Similarly, for the 10 volt scale, it cannot differentiate any between the readings that differ by less than 0.01. That is the meaning here. If you want to measure the 10 volt range, if you want to measure anything less than 0.01, it will not show. It will show only 0.01 volt. That is the meaning here. I am telling you the meaning of these things. The problem what he has given. Okay, anybody want to ask anything on ADC?